Hello everyone, myself Dr. Priya Vashisht, working as an assistant professor with School of Chemistry and Biochemistry, Thapar Institute of Engineering and Technology, Patiala. I welcome you all to the lecture series of phase rule in the subject of applied chemistry. By the end of this lecture, these participants should be able to understand and evaluate the terms phase, components, degrees of freedom, and their correlation to phase rule. The calculation of phases, components, and degrees of freedom will be discussed in detail. And once we are familiar with the terms phases, components, and degrees of freedom, we'll be in position to define phase rule and discuss its implications. Now, the sequential order of the lecture will be introduction to phase rule, then the description of the terms phase, components, and degrees of freedom, and finally the definition of phase rule. Now, before I actually start with the phase rule, we need to recall certain terms we are already familiar with, like states of the matter. Any substance, depending upon the external conditions, can exist in three states, that is solid, liquid, and gas. For example, water can exist in three states, solid, liquid, and gaseous vapors, depending upon the external conditions. Here, each state corresponds to a phase. I will be taking up difference between state of matter and phase of matter after a while. Before I take up that, another term we need to recall and understand is difference between homogeneous and heterogeneous system. You're very well familiar with that homogeneous system consists of a single phase, that is, it has a one phase corresponding to uniform composition throughout the mixture. For example, if we have a saline solution, that is salt solution in water, or sugar solution in water, it is equally sweet. All portions are equally sweet or all portions are equally salty. That means the composition is uniform. While a heterogeneous system has two or more phases present in it, hence forming non-uniform composition. For example, sand, oil and water, or ice and water, that is, one portion will have a different composition as compared to the other portion. The composition is non-uniform. Coming to the basic difference between phase of matter and state of matter. Phase of a matter explains uniform chemical and physical properties of matter. That is, uniformity is both in composition wise and physical properties wise, whereas state of matter explains the form of matter at a given temperature and pressure. Both refer to the different aspects of matter. That is, phase refers to the uniform chemical and physical properties, while matter refers to the form at which that matter will be present, in which form that matter will be present at a certain temperature and pressure. This will be, as discussed in the further slides, will be more clear to you. Now, as I can see that when we discuss phase rule, it's very important to recall that in your lower classes, we have already done chemical equilibrium, ionic equilibrium. In chemical equilibrium, we used to stress upon Le Chatelier principle, and gaseous species were discussed in that. While in case of ionic equilibrium, equilibrium between ions was established. Now, phase rule was put forth by Willard Gibbs in 1874. And this was put forth to judge the behavior of the heterogeneous system when they are in the state of equilibrium. That how do the heterogeneous systems behave when they are in the state of equilibrium? Let's take an example of a heterogeneous system, that solid water is in equilibrium with liquid water. If we increase pressure on this system, what will be the direction of the equilibrium? We cannot predict this direction on the basis of chemical equilibrium and ionic equilibrium both. So here comes the application of the phase equilibrium. or phase rule was proposed in that regard by Willard Gibbs. And phase rule is given by F is equal to C minus P plus 2. F stands for degrees of freedom, C stands for number of components, and P stands for number of phases. I'll be taking up in detail one by one what do we mean by phase, what do we mean by components, and what do we mean by degrees of freedom, and eventually we'll come to how do we calculate this. Now let's start with what is a phase. A phase is a homogeneous, physically distinct, and mechanically separable portion of a system which is separated from other parts of the system via a definite boundary. That is, it is homogeneous in itself, it is physically distinct, and it is mechanically separable portion. Or simply we can say that phase is a state of matter which is uniform throughout, both with respect to chemical composition and physical state. It is represented by capital P in phase rule expression as is mentioned above. And how do we actually calculate the number of phases? I will be taking one by one the examples of different systems and things will be more clear to you. Taking up in the category of liquid in liquid systems. For liquid in liquid systems, if we have two completely miscible liquids, they form homogeneous solution, that is the composition is uniform, and hence they constitute a single phase. Like a solution of alcohol and water, the composition is uniform throughout. And here we can simply imply that polar solvent with another polar solvent constitutes a single phase, and non-polar solvent with another non-polar liquid constitutes another one phase, like a solution of carbon tetrachloride with diethyl ether. Like dissolves like principle works well for this system. Secondly, if mixture of miscible liquids is kept in a closed vessel, above the liquid mixture, there will be some vapors of liquids, hence constituting two phases. One phase is the homogeneous solution of the miscible liquids, and the other phases is the vapors of these liquids present above it, hence two phases. If we consider the case of two immiscible liquids like oil and water or carbon tetrachloride and water, they lead to heterogeneous solution which on standing form separate layers. For example, if I put a mixture of oil and water or carbon tetrachloride and water in a separatory funnel and then make it stand, then a layer will appear after a while that will clearly separate oil from water or carbon tetrachloride and water. They constitute two separate phases. Next, coming to the category of gas and liquid. If the gas is soluble in liquid, like ammonia completely soluble in water and HCl also completely soluble in water, they form homogeneous solution. If I dissolve ammonia in water and on the other hand I dissolve HCl in water, they will constitute a single phase, uniform composition, hence homogeneous mixture. If the gas is insoluble in liquid, like sulfur dioxide in water, it will form a heterogeneous solution leading to two separate phases. For gas in gas system, all gases mix freely, yielding homogeneous mixtures, that is any mixture of gases, may it be oxygen, nitrogen, hydrogen, they form one phase only. Next examples in the category of solid in liquid. If the solid is completely dissolved in liquid, for example, if NaCl or sugar is dissolved in water and the solution is unsaturated, then it constitutes a single phase. Why do I specify the solution is unsaturated? Because there is a certain limit to what we can dissolve a solute in a particular solvent. Once that limit is exceeded, that is, the solution is saturated, the extra solid will settle at the bottom and it will start appearing as a solid and leading to two phases. So unsaturated aqueous solution of NaCl or sugar, it will form a homogeneous solution. If the solid is insoluble, or you can say the solution is saturated of soluble solid like NaCl or sugar, the solution will be heterogeneous. For solid in solid, it's very important, each solid constitutes a separate phase. So in a mixture of solids, that is in a heterogeneous system, number of phases is equal to number of solids. For example, in a particular system, you have n number of solids. Each solid leads to a separate phase. That is, n number of phases is equal to n number of solids. But if the mixture of solids is forming alloys, alloys are homogeneous solid solutions. They constitute a single phase, like copper and zinc to form brass. For example, if we take decomposition of calcium carbonate, that is, if we have a system, thermal decomposition of calcium carbonate. In this, I have written phases is equal to 3 because there are two separate solids, that is calcium carbonate, calcium oxide, and carbon dioxide gas. As I already mentioned, each solid constitutes a separate phase. So two phases are being contributed by two separate solids and one gas. Hence, phases is equal to 3. This is also clear from this image, like carbon dioxide gas and calcium carbonate solid and calcium oxide solid. Similarly, if we consider the decomposition of ammonium chloride, in the decomposition of ammonium chloride, number of phases comes out to be 2. One solid, that is ammonium chloride, and a homogeneous mixture of gases. As I already said, all gases lead to homogeneous mixture. One phase is being constituted by ammonium chloride solid and the other phase is being constituted by homogeneous mixture of ammonia and HCl, leading to phase is equal to 2. And it is very clear from this picture also, like gases constituting a single phase and ammonium chloride constituting another phase. Now, coming to components. What are components? Before I actually come to components, I would very clearly mention that there's a clear-cut difference between constituents of a system and components of the system. If I move to my previous slide that shows the example of decomposition of calcium carbonate or ammonium chloride, in these two systems, the number of constituents are 3. That is calcium carbonate, calcium oxide, and carbon dioxide. Here ammonium chloride, ammonia, and HCl. These are the number of chemical species, individual species, or the number of constituents present in the system. Now, but it is not necessary that if the number of constituents is 3, here also number of constituents is 3, number of components will be 3. No, the components are different from constituents. Now, let's try to define what are components and let's try to understand it in detail. For a system at equilibrium, the number of components is the smallest number of independently variable constituents in terms of which composition of each phase present can be expressed directly or in the form of a chemical equation. That is, out of those mentioned constituents of a system, how many minimum number of constituents out amongst that constituents that we can see in the system, how many minimum number of constituents do I require to express the composition of each phase, either directly or in form of the chemical equation. That is, here I will be considering the relation amongst the different constituents. The components of a system do not necessarily represent the number of constituents or chemical individuals present in the system. And this is represented by C capital in the phase rule expression. Things will be more clear to you as we move further with examples. Now, taking up the examples have been categorically divided into two parts, that is systems involving physical equilibria where no chemical equations are involved. For example, water system has three phases. Water system means ice solid, water liquid and water vapor gas. Each forms a separate phase, that is it has three phases. But the composition of each phase, may it be ice solid, may it be water liquid, or may it be water vapor. The composition of each phase can be represented by a single chemical formula, that is water. So the composition of all three phases can be expressed in terms of one component only, that is H2O. Therefore, this is a one component system, though three phases are present. Let's move to another example, that is sulfur system. It has four phases: rhombic, monoclinic, liquid and vapor. The composition of each phase, that is may it be sulfur rhombic phase, monoclinic, liquid or vapor. This can be expressed in terms of sulfur alone, that is it has again one component system, though four phases are present in equilibrium with each other. Next, aqueous salt solution or sugar solution. When we dissolve salt in water or sugar in water, we get a homogeneous mixture, that is a uniform composition. That sugar solution is equally sweet, all portions are equally sweet, and in salt solution all portions are equally salty. But if I want to express the concentration of the solution, may it be in the form of molarity, may it be in the form of molality or normality, I need to specify the amount of solute in solvent. For example, if I take 10 gram of salt is dissolved in 100 ml of water, or 10 gram of salt is dissolved in 1 liter of water. To express, therefore, the concentration of the solution, we need to specify both the amounts of solute and solvent. Therefore, it is a two-component system. Now, when we come to reacting components, that is where equations are involved, where constituents are related to each other via some equation. There, we need to discuss a formula before we proceed further. The formula states number of components is equal to capital N, that refers to number of constituents. How do we classify number of constituents? Every substance that can be separated from the system. Subtracting from this number of constituents, capital E, that refers to number of independent equations relating the concentrations of N species. This E refers to all the equations that correlate one species of a system with the other species. This will be more clear to you as we proceed with the practical examples. And for the conditions, each independent chemical equilibrium involving the constituent counts as one equation. If there is a one chemical equilibrium, we will subtract 1. If there are two chemical equilibria involved in the system, we will subtract 2. If 3, then we will subtract 3 and so on. If there will be no chemical equilibria involved, then we will subtract 0. If our system contains ions, then a condition of electroneutrality will also apply. That is, a solution will be electrically neutral. Or now simply, we can alternatively define components are number of chemical constituents. Amongst in the system, components are obviously one of the constituents only. Components are number of chemical constituents of the system minus the number of equations relating to those constituents in an equilibrium state. That is, we have to, out of all these constituents, we have to subtract all the equations that correlate one constituent with the other. Now let's proceed further for the examples. First example, if I take, that is thermal decomposition of calcium carbonate. This example I already took up for the discussion of number of phases, and we mentioned that the system has 3 phases. One phase solid calcium carbonate, another phase solid calcium oxide, and another phase carbon dioxide gas. As I already mentioned, each solid constitutes a separate phase, and another phase is formed by carbon dioxide, hence 3 phases. But this does not mean necessarily that the system also has 3 components. The constituents are 3, that is capital N is 3. Now, amongst these 3 constituents, if I take any 2 constituents at one time, may it be calcium carbonate and calcium oxide one time, may it be calcium oxide and carbon dioxide one time, and may it be calcium oxide and CO2. Now let's see, can we express the composition of each phase? Each phase means one phase calcium carbonate, another this calcium oxide, another carbon dioxide. Can we express the composition of each phase in terms of any 2 constituents? If we can do it, it is a 2-component system. Now, let's demonstrate this. For case 1, let's take up calcium oxide and CO2 as constituents. Here in this table, on left hand side, I have mentioned each phase, and right hand side refers to the chosen components, chosen constituents that we expect to be components. Now, when we express this relation between the different constituents of equilibrium, it is permissible to add and subtract the components. Like this, plus 0 CO2, you can see 0 CaO. This is permissible while calculating the components. If we consider the phase calcium carbonate, and we can express its composition in terms of calcium oxide and CO2 very clearly. And another phase calcium oxide, we can express its composition like calcium oxide plus 0 CO2. As I said, it is permissible to add and subtract the constituents. Carbon dioxide, 0 CaO plus CO2. Now, if I consider another case, like if I take calcium carbonate and CO2 as constituents, and again on the left hand side, I write each phase. I mention again, please very carefully, the components are those constituents in which the composition of all the phases can be expressed. So our system is 3-phase system. Our selected constituents should be able to express the composition of all the 3 phases. Like if I take calcium carbonate and CO2 as constituents, the same can be done as is clear from the table. Calcium carbonate plus 0 CO2, calcium oxide, calcium carbonate minus 0 CO2, CO2, calcium carbonate minus CaO. Similarly, the third case also justifies the 2-component system. Calcium carbonate and CaO as taken as constituents. In terms of both of these, all the 3 phases can be expressed as is clear from the table. Hence, it is a 2-component system. If we specify any 2 components, the composition of all the 3 phases can be mentioned. Let's make it more clear by taking another example, that is dissociation of ammonium chloride. For the dissociation of ammonium chloride, it is ammonium chloride solid in equilibrium with gases, that is sublimation is considered, and that ammonia gaseous and HCl gas is formed by the decomposition. Now here 2 cases arise. If the dissociation of ammonium chloride is taking place in a closed vessel, this implies that partial pressure of ammonia is equal to partial pressure of HCl because the vessel is closed. And this is a case when gaseous mixture is formed by sublimation of ammonium chloride solid. Now this system has 2 phases. One phase is being constituted by the ammonium chloride solid, and the other phase is being constituted by the homogeneous mixture of the gases. As I already told, all gases constitute a homogeneous mixture. Now, an equimolar mixture of ammonia and HCl the system is closed, an equimolar mixture of ammonia and HCl in the vapor phase. It may be regarded as ammonium chloride in the vapor state itself. What do we imply from this? That is, the constituents of the mixture are present in the same proportion as they were combined in solid ammonium chloride. Therefore, the composition of each phase can be represented by ammonium chloride alone, forming one component system. But if the system is open, that is in an open vessel, it implies that partial pressure of ammonia is not equal to partial pressure of HCl. Or we can also say that to the system, if we introduce excess ammonia or excess HCl, then what is the number of components? In this case, when there is open vessel, the system becomes a two-component system because partial pressures of gases are no longer same, and the composition of vapor phase can no longer be expressed in terms of ammonium chloride alone. Here again in this table, on the left hand side, phases are present, and on the right side, components. For solid ammonium chloride phase, component is ammonium chloride. For ammonia gas plus HCl gas equimolar mixture, this is another phase that is homogeneous. We can express it in terms of ammonium chloride gaseous. But if the system is taking place, the composition dissociation is taking place in an open vessel, that is ammonia plus HCl gas and excess ammonia is added. Now we cannot express the composition of this system, of this phase, in terms of ammonium chloride alone. We need to specify the amount of ammonia also. On the other hand, if I take ammonia gas plus HCl gas and excess HCl is introduced, I need to specify the amount of HCl. Hence, it forms a two-component system. Now, if I take another example, a very important example, system of sodium chloride in water system. If the solution is unsaturated, I also mentioned this previously, unsaturated aqueous solution of NaCl, this is one phase, two component system. One phase because once we dissolve sodium chloride in water, it is completely soluble and it forms a homogeneous mixture. The composition is uniform throughout, but the number of components is two because I need to specify amount of NaCl dissolved in which amount of water, may be it in terms of any concentration parameter. So this is a two-component system. For saturated solution of NaCl, the phases will become two because the excess NaCl that cannot be dissolved will settle down at the bottom, will separate out as a solid, and the phases will be two. It has two phases. Aqueous solution of NaCl forms the one phase, that is homogeneous, and solid NaCl leads to another phase. Also, the composition of both can be expressed in terms of NaCl and water. Hence, it is a two-component system. Therefore, we have to be very careful whether it is unsaturated aqueous solution or it is saturated aqueous solution. The system remains two-component only. The number of phases change. Then this again table clearly depicts what I already explained. Aqueous solution of NaCl is one phase, can be expressed in terms of amount of NaCl and amount of water. Solid NaCl, amount of NaCl plus zero water. As I already mentioned, it is permissible to add and subtract. This is clearly depicted in this picture. This is the solid NaCl that is not dissolved for a saturated solution and it settles down and leads to another phase, and the solution of NaCl in water forms the another phase. Now, to clearly indicate that, to develop what level of understanding have we put in, let's calculate the number of phases and components for the following systems. Mixture of N2 and H2 contained in a vessel. Another example, for equilibrium, carbon solid, carbon monoxide gas, carbon dioxide gas, and oxygen gas. Let's take it one by one. For first example, that is mixture of nitrogen and hydrogen contained in a vessel. All gases, I told you, they form a homogeneous mixture. They are miscible. So phase is equal to 1. But components will be 2 because concentration of both nitrogen gas and hydrogen gas has to be specified to define the system completely. In the second case, number of phases will be 2. One phase will be constituted by the carbon solid and another phase will be constituted by the homogeneous mixture of the gases present. The number of components will be 2, that is carbon and oxygen, because to express the composition of each phase, may it be carbon, may it be CO gas, may it be carbon solid, and may it be homogeneous mixture of gases, we can specify the composition in terms of carbon and oxygen only. Now let's take up another example. This is a very important example, that how do we justify KCl NaCl water system is regarded as a 3-component system, while KCl NaBr water is regarded as a 4-component system. This is a clear example of the application of the formula we used, C is equal to N minus E. Now for KCl NaCl water system, N is equal to 3, that is the number of constituents is 3. There is no independent equation that correlates the concentration of the constituents, that is, there is no equilibrium, hence E is equal to 0. Now if we apply C is equal to N minus E, the following conditions will exist, that is N is equal to 3, E is 0, and hence it forms a 3-component system. While in the case of KCl NaBr water system, N is equal to 5, that is KCl NaBr water, and apart from that KBr and NaCl will be formed according to the equilibrium KCl plus NaBr in equilibrium with KBr plus NaCl. So this one relation is the equation that correlates the constituents with each other, and hence we refer this as number of independent equations is 1, that is E is equal to 1. Therefore we can calculate the number of components as C is equal to N minus E. N stands for number of constituents 5, minus 1 is equal to 4. Therefore, it is a 4-component system. Let's move to another example. Calculate number of phases and components in the following system. Copper sulfate pentahydrate solid in equilibrium with copper sulfate trihydrate plus 2 moles of gaseous water. In this case, the phases is equal to 3. One solid constitutes a single phase, second solid another phase, and one gaseous phase. While the number of components is 2, because the composition of each phase, may it be copper sulfate pentahydrate, may it be copper sulfate trihydrate or gaseous water, can be expressed with the help of 2 components, that is copper sulfate and water. Therefore, it is a 2-component system. Now, next, once we have already discussed in detail the number of phases and the number of components, we are in position to discuss the degrees of freedom. What do we mean by degrees of freedom? The degree of freedom of a system is defined as the minimum number of independent variables. Variables, when I say, it means temperature, pressure, and concentration or composition, which must be specified in order to define the system completely. It is represented by F in the phase rule expression. As I already mentioned, F is equal to C minus P plus 2. Once we know the number of components in the system, the number of phases in the system, we can easily calculate the degrees of freedom. These are the minimum number of independent variables such as temperature, pressure, and concentration, which must be specified. So let's understand this more with the help of examples. But if the system we calculate comes out to be with F is equal to 0, we call it as an invariant system. If F is equal to 1, it is univariant or monovariant system. If f is equal to 2, it's bivariant system. If f is equal to 3, it's trivariant system. Now let's come to the example. Let's take up the example of a univariant or monovariant system first. Consider the heterogeneous equilibria, water liquid in equilibrium with water gas. The system will have only 1 degree of freedom. What does it mean? It means because at a given temperature, the equilibrium vapor pressure of water can have only one fixed value. Therefore, if we specify the temperature, pressure becomes known automatically and vice versa. That is, for this equilibrium at a given temperature, there is a single equilibrium vapor pressure that can exist, and therefore if we specify temperature, pressure automatically gets specified. Therefore, it has 1 degree of freedom. In the category of bivariant system, for example, for a pure gas, you apply ideal gas equation, that is PV is equal to RT. If pressure and temperature are specified, if P and T are specified, there can be only one definite value of volume, that is volume gets automatically fixed. Hence, for all gaseous systems, for the gaseous system, 2 factors must be stated in order to define the system completely. Hence, it is a bivariant system. For trivariant system, if we take mixture of 2 or more gases, it is completely defined only when pressure, temperature, and composition are specified. If pressure and temperature are specified, the third variable, that is composition, may be varied. Since it is necessary to specify 3 variables to define the system completely, even if we specify pressure and temperature, the composition can vary. Therefore, we need to specify 3 variables to define the system completely. Hence, there will be 3 degrees of freedom, that is trivariant system. If I talk of non-variant system, the water system, that is water solid in equilibrium with water liquid, in equilibrium with water gaseous, the system will have no degree of freedom. The reason is that these 3 phases can exist or coexist only at one particular temperature, that is freezing point of water, and under one particular pressure only. That is triple point is being defined at a single temperature and pressure. Since both the variables are already fixed, the system automatically gets defined and there's no need to specify any variable, making it a non-variant system. If we take up the cumulative examples to calculate the degrees of freedom, via these examples, we'll be able to recall again to evaluate the number of phases, components, and degrees of freedom in one go. Calculate the number of degrees of freedom for the following systems. A solution of a solid in a liquid in equilibrium with solvent vapor. Now, if a solution of a solid in a liquid in equilibrium with solvent vapor, the formula implies F is equal to C minus V plus 2. Now, the number of phases, first of all, if we see, the number of phases is 2. One is solution of solid in liquid, that forms a one phase miscible homogeneous mixture, and another phase being the vapor in equilibrium with the solvent vapor. So there are 2 phases. For the calculation of components, the components is 2, that is, I need to specify the amount of the solid dissolved in a particular amount of liquid. Now, once we know the number of components, the number of phases, we are in position to calculate degrees of freedom, that is bivariant system. Taking another example, thermal decomposition of magnesium carbonate. This example resembles the thermal decomposition of calcium carbonate example we already took up. Now, this system has 3 phases, 2 solids and 1 gaseous phase. The number of components is 2. Magnesium oxide and carbon dioxide. It can be magnesium carbonate CO2, it can be magnesium carbonate MgO, as I already discussed with the example of calcium carbonate. So number of components is 2. And if we calculate the degrees of freedom, it comes out to be 1. That is, this is a univariant system. If ammonium chloride is allowed to dissociate in a vessel already containing some ammonia gas, what is the value of degree of freedom? If we recall, I discussed in detail with you the example of ammonium chloride dissociation in an open vessel and in a closed vessel. And this is a case where excess ammonia is already there. F is equal to C minus P plus 2. The number of components will be 2 because we need to specify the amount of ammonia also along with the ammonium chloride. And the number of phases will be 2. One contributing ammonium chloride solid and the other ammonium chloride gas plus ammonia gas, considering the sublimation phenomena. Hence, with the help of these cumulative examples, I expect that the concepts are clear to you all and you will be in a position to evaluate the number of components, phases, and degrees of freedom. And in the upcoming videos, that is in the continuation of the series, we'll be taking up one component system and two component system in detail. Thank you.